Hello everyone, welcome to the NPTEL online course on electric vehicles. Let us discuss the next topic under Introduction to EV, which is hybrid electric vehicle systems and their configurations. So, a battery electric vehicle is one of the most promising technology for road transport. It is due to many reasons. It has higher energy efficiency compared to hybrid electric vehicle or IC engine based vehicles. It allows diversification of energy resources. It means the electricity needed to charge the batteries can be obtained by oil, gas, coal and all the renewable sources such as solar, wind, etc. Under V2G operation, it supports power system for load equalization. So, it can support peak shaving during peak load demand, or it can support coordinated charging during night hours or light load. So, it has a zero emission vehicle and it creates very less emissions even globally. So, when the electricity used for charging the battery it's derived from thermal power plants, then there is a possibility of SO2 gas emissions. But otherwise, if large part of charging energy is derived from renewable energy, then it is totally a zero emission vehicle. So, it is a very quiet operation possible in a BEV. So, IC engine based vehicles are typically noisy. So, the main drawback which is hindering the success of BEV are short driving range. So, we all know that the energy content that can be stored in a vehicle using batteries and other resources is very low. So, you cannot drive a very high driving range using a BEV. So, the battery cost is high, and if you use a large energy content using lot of batteries, then it is also costly. Secondly, we require a battery replacement after a cycle life of maybe 5 years, so which is again adding to the cost of electric vehicles. Charging, as we have seen, is one of the very important thing for a BEV. So, battery needs charging, and that also causes charging time to be available to the customer. Secondly, the requirement of charging infrastructure, which is not there at present in the large scale as compared to the filling stations for IC engine based vehicles. So, all these limitations are hindering the growth of BEV as a mass scale vehicle. So, what is the solution? So, hybridization of resources is one of the key element which is generally looked into. So, we have already seen that there is a possibility of using one or more energy resources within a BEV. So, we have explored that if you use fuel cell which has high specific energy and ultra flywheel which is high specific power or other things together, is possible to increase the driving range and even get a performance similar to a IC engine based vehicle. But the limitations what we have seen in a battery driven vehicle still remains. So, therefore, we have to look for another alternative which can solve drawbacks. So, another option is why can't we go for hybridization of drivetrains? Means is possible to connect a IC engine based vehicle and its drivetrain to the drivetrain of an EV such that we can get better performance for a IC engine based vehicle together with solving the limitations of battery electric vehicle. So, this is an interim solution and it may be a quick solution to solve for fuel economy of IC engine based vehicle together with less emissions causing pollution and health hazards. So, what a hybrid electric vehicle can do? A hybrid electric vehicle which is a hybrid vehicle that utilizes both the IC engine and electric motor within the same vehicle. So, since the IC engine based propulsion is attached to the hybrid electric vehicle, the range anxiety will not exist anymore. Secondly, since we have filling stations which can readily give petrol or diesel for the vehicle, so the fueling infrastructure is also taken care of and we need limited resources for battery charging. So, it is not a zero emission vehicle, but the emissions are lesser than a full IC engine based vehicle. In addition, we can see that now the IC engine efficiency may be better and it may be taking less fuel for driving the total vehicle. So, the only price we have to pay is now the system will be complex and it has to be handled properly such that all these benefits can be obtained. So, in a hybrid electric vehicle, we are combining the efficiencies of a IC engine vehicle and a battery electric vehicle. So, let us see the powertrain efficiency of individual IC engine vehicle and electric vehicle. So, in a IC engine based vehicle, if we assume a energy input of 100%, the major loss happens as heat energy. So, 62% of the energy input to a IC engine is wasted as heat energy. Secondly, a good amount of loss, which is 17%, happens when the IC engine is left idling. So, this is required because a IC engine is not able to start and stop at very frequent times, so that the efficiency is best. So, we have a mechanical losses which are known as driveline losses of 6% in a IC engine based vehicle. So, in totality we can see that the effective energy which is available in the shaft is only 15%. If we see the similar thing in a EV powertrain and we start with energy input of 100%, a EV powertrain generally faces a electrical loss of around 14% and a driving line losses which is 6%. So, it can be even lesser if we use a very high performance EV which does not have gears or which does not have a differential. So, it can be even lesser. So, typically we get the effective energy utilization of 80%, which is very high compared to a IC engine based vehicle. So, when we combine these two things in a common vehicle or the same vehicle which we are now terming as a hybrid electric vehicle, we have to see that how the losses of the IC engine based powertrain can be minimized. So, there is a scope of improving the engine efficiency, because it is not alone now, it has a support of EV motor. Secondly, can we do something for decreasing the loss due to idling operation? So, the energy efficiency improvement is possible in a IC engine based powertrain by incorporating a feature which is known as start stop feature. So, the engine is no longer needed to keep idling, and it can be stopped whenever supposed to. So, this feature enables 6% saving in energy. In a hybrid electric vehicle, there is also a possibility to store the regenerative braking energy. So, this can add another 6% to the energy savings, and we can say that if we have these two features, roughly we are saving 12% of the energy. As we have said earlier, the IC engine has a major loss component as heat energy. This is due to the inefficient operation of IC engine. So, this can be improved by operating the electric motor such that the IC engine can now operate at its best efficiency. So, there is also a possibility to increase another 15 to 20%, and it is possible to get energy saving in the range of 25 to 30%. So, we can say that incorporating a EV powertrain with a IC engine based powertrain improves the energy spent in the vehicle by around 30%. So, as the data shows, this kind of energy saving is even better for a urban driving compared to a highway driving. So, let us see the energy map of a typical EV electric motor. So, if a electrical machine is the sole propulsion device in a, let us say, in a battery electric vehicle, it has to support all the modes of operation. So, it has to support constant torque region, and also has to support constant power region. So, let us assume that 250 Newton meter torque is required, and a speed of around 600 or 6000 RPM is required. And let us say we start the constant power region somewhere around 2500 RPM. So, the efficiency map has to be designed such that the electric motor operates at maximum efficiency in most of the regions. So, this is a important research area, and so the typical energy map is something like that. So, we generally get the highest efficiency around this region, which is, let us say, 92%. And then we will get another region which has, let us say, efficiency of 90%. And let us say we have another region which has a efficiency of 80%. So, this is an energy map. So, when an electric motor is designed, it has to be taken care that the efficiency is maximum in wide speed and torque ranges. Similarly, in a IC engine based vehicle, there is a fuel consumption map, which gives an indication of the fuel economy or fuel consumption. So, let us say it's the highest so 60 Newton meter torque that can be obtained from a IC engine based vehicle, and we are operating at a maximum speed of again 6000 rpm. So, typically this is the region of operation, and we have pockets similar to the efficiency thing. And these regions tell the fuel consumption. So, let us say it is 210, 220, 210, this is 240, 270, 350. So, this is basically energy consumption in gallons per kilowatt hour. So, the best fuel economy or the least fuel consumption is possible when we operate the system in a region or line which is known as OOL or optimal operation line. So, in a hybrid electric vehicle, the power flow between a IC engine and electric motor is designed such that we obtain maximum fuel economy for a IC engine, minimum system cost and good driving performance. So, all these things are considered while deciding a control strategy. So, when we design the drivetrain of a typical HEV, we see that the system always operates such that the fuel economy is maximum and the emissions are also minimum. So, we always operate in OOL line such that each operating point in the region in a torque speed plane enables that operation. So, we also should look at minimum engine dynamics. A typical IC engine based system does not give good fuel economy and also lead to higher emissions if the load fluctuations are maximum. So, we should see that the high dynamic operation should not be obtained from a IC engine, rather it should be supported from a electric motor. Similarly, the engine should not be operated at very low speeds. So, at very low speeds again the emissions are very high and the fuel consumption is also very high. So, when the engine speed is below a certain speed, it is better to stop the engine. So, engine needs a minimum turn on time, rather it is set so that once you start a turn on operation, the user should not give a turn off command until the turn off process is complete. If we do not do that, there is a possibility of heavy emissions and carbon formations in the engine, which is not good for the health of an IC engine. So, the battery voltage has to be kept in a good condition. So, we need a battery and a integrated starter generator or the coupled motor for starting the IC engine. So, the battery has to be kept in a good condition such that it enables starting of the IC engine properly and the required acceleration. So, power distribution between the IC engine and the electric motor should be designed to suit the driving cycle of the vehicle. So, what are the different types of hybrid electric vehicles? So, conventionally only a series hybrid and parallel hybrid type of HEVs were designed, but later more advanced HEVs such as series parallel operation and complex operation is possible with the new age technologies, and these are very popular in high end electric vehicles, especially the hybrid electric vehicle. So, let us see the configuration of a series hybrid electric vehicle. So, we can see that a IC engine based system is connected to the battery electric system using a electric generator. So, the power for the battery is generated by running the IC engine, and the mechanical energy obtained by the IC engine is converted to electrical using electrical generator, and it is used for charging the battery and driving the electric motor for propulsion. So, as the propulsion device is electrical, we do not need any clutches, which is typically required in a IC engine based vehicle. Therefore, the placement of the IC engine and the generator is flexible and it can be placed anywhere. So, this system is very simple to make, but it has few drawbacks such that it now needs 3 mechanical systems, and the sizing of them has to be high when you are demanding a high climbing operation or high acceleration. So, this is known as a IC engine assisted electric vehicle. So, it is also possible to have another configuration which is known as parallel HEV, where both the IC engine and the electric motor are used for propelling the system or the transmission. So, in this system we need to have 2 clutches, one for connecting IC engine to the transmission and another for connecting motor to the transmission. So, this system is called a dual clutch mechanism. Here the advantage is that the sizing of each of the propulsion system is lesser compared to the series system. Also the size of the battery can be also less, but now the system is slightly more complex. To obtain the features of both the series and parallel hybrid in the same HEV, a new configuration known as series parallel HEV was developed. So, compared to a series HEV, now a mechanical link is also added between the IC engine and the transmission, and compared to a parallel HEV, a electric generator is connected between IC engine and the power converter. So, this system can obtain all the operation that is possible in a series HEV or a parallel HEV, such that the more better performance and the fuel economy of IC engine can be obtained. Nowadays, complex hybrid EV configurations is becoming popular for high end HEVs, where there are 2 changes compared to series parallel configuration. First is, now the motor operates both as propulsion system and supporting the IC engine. Secondly, it can also work as a generator for charging the battery. So, this machine now has a dual purpose. Secondly, we need a power converter here, another power converter if we want to use this motor as propulsion device for supporting the IC engine. So, as we can see now there are 3 propulsion devices, 2 motors and IC engine. So, it is possible to operate all these propulsion devices in tandem, and we can operate in a very high torque mode during starting. This kind of configuration is generally used for dual axle transform. So, the one of the propulsion devices such as IC engine is connected to the front wheel system, and a electric motor is connected to the rear transmission system. So, another simplicity of this system is now the requirement of propeller system which shift the power from the front wheels to the rear wheel in a typical series or parallel system can be eliminated. So, the system is less heavy. Secondly, the placement of the system is more flexible, and the sizing of each component can also be reduced. Another important thing is now the energy can be recovered from all the wheels during braking. So, there is also an increase in energy recovered during braking operation. So, it is possible to connect either this system as front engine rear electric type, or is another configuration where the front wheels be driven by electric and the rear transmission is driven by the IC engine. So, let us stop the discussion for HEV subsystems here. So, in this interaction we have seen the benefits of HEV compared to a BEV, and what are the different types of configurations we generally use to make a HEV, which includes designing the control strategy for a IC engine based system and the placement of this individual propulsion system and their connection to each other. So, we will discuss the different modes of operation of each of these configurations such as series hybrid, parallel hybrid, series parallel hybrid and complex hybrid in different modes of a electric vehicle such as starting, normal driving, acceleration, deacceleration, battery charging, etc. in our next interaction. So, thank you for listening.